Hello and welcome, everybody. Welcome to this science, astrophysics, cosmology, etc. episode of the Ask Abhijit show. I'm going to have a smaller audience today. I know that, but that's perfectly all right. This is my favorite topic. This is the topic, essentially. So I hope you're all doing great. And welcome to everybody. Let's see who all is there in the live chat right now. I can see Tommy Versetti, Yash Tiwari, Ankit Mishra, Ed Brown, Anurag Jha, Joydeep, Feminist Slayer, Om Bekherikar, hello, Gameaholic, Geopolitical Dubey, Sonal Kumari, Hemal Nandi, Nikhil, Random Skull, Vivekananda Reddy, Ankita Kachap, Jippy Phoenix, Anvit Shetty, Kanan Dhanaraj, Pulkit Grover, Sujal MS, Amit, Samarth, Priyanka, Javalia, Anurag, Ja, Nikhil, Xander Toretto, Utkarsh, Zin, Jay Guman, Komal, Vivekananda Reddy, Megdeep Methi, Vedanta Kulkarni, Falcon, Anvit Shetty, Zubong Izung, Chirag Kothari, Brian Lord, Ayush, Sarthak Sharma, Neo Wise, 45, King Guli, Vishakha Kabila, um, and who else? Mihir, Prithwin, God, Usop, Jatin Singh, and many, many other people. So, welcome to all of you. I will not greet all of you individually because it's not possible to do that. But thank you so much for being here. So, this is going to be a session in which I'm going to take questions that you have asked in the comments. And this is going to be kind of a different session. I'm going to take 10 to 15 questions maximum because we're doing this much more frequently. So I'm going to take the best questions that you have asked. Thus far, I have been doing in the past year or so, I don't know, 30, 40 questions I'm taking. I think we're going to cut down on that. I'll take 10 to 15 questions at most, your best questions. So if you want me to answer your questions, ask the best possible questions you can. And what do I mean by the best questions? It means questions that will benefit everybody, questions whose answers will benefit as many people as possible. So ask your best questions. So I'm going to take 10 to 15 questions from the comments, and then I'm going to take maybe 5 questions from the live chat when the show is winding down. All right, so that's how I'm going to play this today. So let us go into the questions. What questions do we have today? What mix of questions do we have? Here we go. Aviral Chauhan says, why does inflation 10 raised to minus 36 seconds after the Big Bang still have a high uncertainty, even after cosmic microwave background radiation imaging? Also, is there eternal inflation not just at the Big Bang? All right. So, what is inflation? What is this cosmic cosmological inflation? And does it not work? I mean, does it have a high uncertainty? I'm assuming what he's asking by what he means by high uncertainty is that we don't have evidence of that. Is that so? So, it's a long answer. So let's take it step by step. First of all, cosmic inflation is part of the Big Bang theory, but it was not part of the initial Big Bang theory. The initial Big Bang theory was based on a couple of rules, a couple of principles. First of all, that the rules of general relativity is the framework. General relativity is the framework set of rules that governs the universe. That was the first uh, consideration of the Big Bang theory. And secondly, the Big Bang theory was about taking the data into account. Whatever data we have data, we have observational evidence that the galaxies are all receding, they are all moving away from us, and they are moving away from us at speeds that are proportional to their distance from us. So the further away the galaxies are, the faster they are moving away from us. So that's the kind of i- information that we had. So based on this, what we saw is that if we take these things into account, then uh, certain logical considerations come out of this. So, for example, as per general relativity, if you fill the universe with matter, which we know is there, matter and energy, light and radiation and all that, and if it is reasonably evenly distributed, as we know it is at the largest scales, then that universe that you are constructing in this manner, it will not remain static. Like the Fred Hoyle, Janet Narlikar theory, steady state theory, it won't remain static. It must either expand or it must contract. Okay, so it's either an expanding universe or a contracting universe based on this, and we know it's an expanding universe based on observational evidence. And then what you do is you go backwards in time. You extrapolate this backwards in time, and that was the big idea of the Big Bang. The Big Bang Theory. So the Big Bang Theory makes a number of predictions, okay, and I'm not going to go into the details of that, but these predictions have been verified. And that's why the Big Bang Theory, what we call the Big Bang Theory, is the theory that works. It is the best theory that we have right now. Okay, all the other theories, whichever they are, they kind of have faltered here or the other, but the Big Bang Theory works. But there are certain predictions of the original Big Bang Theory that did not work. For example, look, once the Big Bang happens, this alleged explosion, it's actually an expansion of the universe. But once this happens, you have the universe, the various components and parts of the universe that move apart from each other. And this happens over billions of years. So you have large areas of the universe that have not been in contact with each other for 13.8 billion years, let's say. So therefore, if you look in different directions in the universe, you should see different temperatures. Different parts of the universe at different temperatures, right? Logically makes sense, but it's not there. It's all uniform, same temperature everywhere. Why is that? And then, as per the Big Bang, there should be in the very early uh, part of the universe, the very early let's say time period of the universe, there should have been the production of exotic weird particles like magnetic monopoles, etc. Well, where are they? We have never discovered a single magnetic monopole anywhere, right? And then the universe should have spatial curvature. It should be curved, but it's a flat universe that we see. What do I mean by a flat universe? The flatness problem. Why is the universe flat? What do I mean when I say that the universe is flat? See, let's say you have a ball, okay, a spherical object. On a spherical object, if you take 3 points, it should draw a triangle, right? Yes, should draw a triangle. Now, the geometry that we learn in school, it says that when you have a triangle, the sum of the 3 angles is what, 180 degrees? 180? I think it's 180, right? But in curved space, it could be more than 180 or it could be less than 180, depending on the curvature, if it's positive or negative curvature. But what we see is that it's essentially flat space. The universe is flat. If you draw a triangle, 3 very far apart objects, you're gonna see the sum of the angles is 180. So you have a flat universe. There is no measurable curvature. So these are the problems with the Big Bang Theory, and that's where inflation comes in. So inflation was proposed by Alan Guth in 1979, 1980. I think the paper came out in 1981, but it was proposed. The idea popped into his head in 1979. Okay, so inflation is what solves these problems. So inflation is this state of the universe that is before. Well, it's a very very initial part of the Big Bang, essentially before the Big Bang, you could say. So you have a very early universe, and then there's inflation, and that's kind of the Big Bang. So in this inflationary state of the universe, the dominant form of energy, according to this theory, wasn't matter, it wasn't radiation, it wasn't all of that. It was the dominant energy was inherent to the fabric of space itself. Okay, space itself was full of energy, and it had a tremendously high energy density. Okay, and this incredibly high energy density that was inherent to the fabric of space itself, that is what caused the universe to expand rapidly. And it was not just rapid expansion, it was superluminal expansion. The fabric of space or space-time expanded faster than the speed of light itself. So you can break the speed of light if it is space-time itself that expands. So that can expand at any speed. So that was the thing, superluminal expansion. Okay, and so this caused the universe to expand ridiculously rapidly, superluminally rapidly, and this caused the universe to be stretched so large that it essentially became indistinguishable from flatness. Okay, and because it expanded so rapidly and so on, so that's why if you look at the universe in different directions, if you look at various parts of the universe, then we will see the same properties everywhere, uniform properties of the universe everywhere, because they all originated from a previously connected state in the very beginning. Okay, and also when inflation ends, okay, inflation is not something that goes on forever, it ends at some point in time, and it did end. So when this ended, all this energy that was inherent, that was part of the fabric of space, it transformed into matter and antimatter and radiation and whatnot. And and by this process, we also avoid the production of exotic particles, magnetic monopoles, etc. But magnetic monopoles could still exist, but it's just that we have not found them. Maybe they are stretched, they are they are spaced very, very far apart, and so on. So that is inflation. It solved the problems of the Big Bang, of the original theory. So it is kind of an addendum to the Big Bang theory. It is something that we attached on top of the Big Bang theory. But yeah, it makes predictions that many of these predictions have been verified. So quantum fluctuations, for example, it says that quantum fluctuations during inflation, quantum fluctuations is it comes out of quantum field theory. uh, you can kind of violate the Heisenberg uncertainty principle as long as you do it within a certain time frame and so on. So quantum fluctuations during this period of inflation would produce the seeds of density fluctuation. So you have, if you look at the universe at the largest scales, it's kind of homogeneous, isotropic, and all that. But if you look at it at smaller, more local scales, you have, you know, fluctuations of density. You have galaxies and clusters of galaxies in some places, and some places you have voids. There's nothing in there except for maybe interstellar medium, protons and electrons and all that. So why is it like that? It's because of the fact that the quantum fluctuations in the very early universe during the inflationary phase, they produced the seeds of today's density fluctuations. So all of those over densities, they could also have produced micro black holes and all, but that's a different story. So those fluctuations, quantum fluctuations in the very early phase during inflation, they eventually gave rise to all these regions of high and low density and galaxies and all the structure that we have in the universe. Okay. And one of the predictions of inflation is that the universe should should be filled with we know we have cosmic microwave background radiation, CMBR. We have the CMB, cosmic microwave background, which is the background of the electromagnetic waves. It's light, it's photons. Similarly, there should be a cosmic gravitational wave background. Primordial gravitational waves should be all around us. The universe should be filled with these primordial gravitational waves. And these primordial gravitational waves should actually imprint themselves on the cosmic microwave background as something that's called B modes. And there was a false positive detection of this, the bicep 2 experiment. Yeah, there was a famous video out there on YouTube and so on. So that's not yet been proven, but a number of things have been proven. And obviously flatness, the universe should be almost nearly flat, but not quite perfectly flat, and a little bit of that could be there. So that is what inflation is. So it is not something that has a high uncertainty. Lots of evidence of inflation has been found. It solves the problems of the original Big Bang theory. It improves it significantly, right? So that's what it is. Eternal inflation, not just a Big Bang. Well, in that we have to delve into different theories. Maybe there is inflation that goes on even eternally and so on. But overall, the point is inflation is the best theory that we have if we attach it on top of the Big Bang theory. It essentially accounts for the state of the universe the way we see it today. All right. Okay. Next question. Pranav Hariharan says, "What is the cosmic dawn and epoch of reionization in cosmology?" The cosmic dawn. So the cosmic dawn it refers to this period in the early universe. Now we are no longer in the inflationary period, but we are still in the early universe phase. So the cosmic dawn is that period of the universe, its history, when the first stars and the first galaxies began to form, and they began to light up the cosmos. It's a very early universe still. Okay. So before this cosmic dawn, when the first stars and galaxies began to light up the universe, there was something called the cosmic dark ages, the dark ages of the universe. And this was a time after the first cosmic microwave background radiation, the CMB was emitted. Of the first CMB, the first light was emitted about 380,000 years, roughly after the Big Bang. Okay. So the first CMB, the first cosmic microwave background, the relic, the afterglow of the Big Bang is emitted about 380,000 years after the Big Bang. And that is the end of the dark ages of the universe. Now, what are the features of the cosmic dawn? So you have the formation of the very first stars. Okay, these are called the first generation stars or population 3 stars, and these are composed almost entirely of hydrogen and helium, as the heavier elements had not yet been formed. See, all the heavy elements that we know of, we have blood in our veins. What is in the blood? What makes the blood red? Hemoglobin. What is the thing that makes hemoglobin red? It is iron. Okay, iron is a heavy element. Now, iron, how is iron formed? Iron is formed when stars die. When a star starts producing iron through fusion, that is the death knell of a star. Because no matter how large and big and all that a star is, it simply can't fuse iron. And that is, iron is like, it's like poison for a star. The moment it starts producing iron, its life is measured in milliseconds. Uh, so iron comes from stars, calcium, oxygen, nitrogen, everything comes. All these elements, they formed inside stars. But when we're talking about the first stars of the universe, at the cosmic dawn, the population 3 stars, then it was all hydrogen and helium, because hydrogen fuses to form helium, and that's how the first light came out. Okay, I mean, the first stars lit up. So these are the very early stars that were part of the cosmic dawn, and these were very massive stars. We believe these were very massive stars, and they were very short-lived stars. And then the light from these first stars, it began to ionize the surrounding neutral hydrogen. So at this time, there was hydrogen everywhere, neutral hydrogen, not ionized hydrogen. It was neutral hydrogen. So the light from these first stars began to ionize this neutral hydrogen. What do I mean by ionizing hydrogen? It means break the hydrogen atoms apart. And what comes out? A hydrogen atom, the standard hydrogen atom, not the heavier isotopes. The standard hydrogen atom, protium, has 1 proton and 1 electron, and that's it, no neutrons. So when you ionize that, you essentially get a free proton and a free electron. Okay, so the light from these first stars began to ionize the surrounding neutral hydrogen, and this was the transition from the dark ages to a universe filled with light. And then with the first stars, eventually after a while, you have the formation of the first galaxies, the first proto galaxies, and these would have been initially pretty small, and they are formed from the gravitational collapse of gas, and dark matter was obviously there. Yes, dark matter, well, yeah, dark matter as well. So overall, this is what leads to the formation of larger structures over time. Okay, so that is the cosmic dawn. The other question is, what is reionization? So reionization is this period in which the predominantly neutral hydrogen in the universe was replaced. It was reionized by the first luminous sources, which is the first stars that we just spoke about. The first stars, their light it ionizes the predominantly neutral hydrogen in the universe. So this is something that comes directly after the cosmic dawn, because until this light comes from the first stars, the hydrogen will remain neutral. Okay, so this is what reionization is, the epoch of reionization. It immediately followed the cosmic dawn, and this fundamentally changed the state, the nature of the universe. Okay, so the first stars form, and it is the higher frequency photons from these stars that are capable of ionizing hydrogen. Because see, it's light. The stars are giving off light. If you have a sun like star, let's say, you have white light predominantly, but you have light in other frequencies as well. And it is the higher frequency light, the more energetic photons, that are capable of actually dislodging an electron from a hydrogen atom. Okay, so it is the ultraviolet light, the energetic, the more energetic light from these stars that split the hydrogen atoms and ionize them. And this gradually made the universe transparent. It was, before that, it was opaque. And you had bubbles of ionized hydrogen that formed around the first stars and the first galaxies, and these bubbles eventually overlapped, which gave rise to an ionized intergalactic medium. If you look at space today, it's full of, it's almost a vacuum, and you have cosmic microwave background radiation in there, 2 point something Kelvin, but you also have ionized hydrogen, which is protons and neutrons, flying around. So that all originated from that time. Okay, so when did reionization begin? The exact timing is kind of unknown, but it's between half a billion and 1 billion years after the Big Bang, and it was most likely a gradual process, starting with uh, with isolated regions of ionized hydrogen, and eventually over time progressing into a universe-wide reionization. So it's a gradual process, maybe half a billion years after the Big Bang, maybe a billion years, and maybe the whole process took half a billion or a billion years. So that is the cosmic dawn, and that is the epoch of reionization in cosmology. It helps us understand how the first stars and galaxies and black holes also formed, how the all of these structures, how all of that formed structures, larger structures, like galaxies, like clusters of galaxies. And then obviously at the largest scales, you have these filamentary structures that are mediated by dark matter, and which we can kind of we can deduce their existence through gravitational lensing and all that. So all of that, so that's why it's important to it is key to understanding how the universe evolved, and it helps us understand the timeline, the history of the universe. And the interstellar medium also helps us understand uh, the formation of galaxies, the propagation of light, and all that. So yeah, that is the cosmic dawn, and that's the epoch of reionization in cosmology. Next question is by Akash Bullar. So, in case you people, I mean, many of you must be more recent subscribers, but when I started the Ask Abhijit show in the very beginning, I think in the year 2021, Akash used to ask a lot of questions, very good questions. I used to take a lot of his questions. It kind of upset lots of people that I took so many questions from Akash, but he asked so many brilliant questions. And he was also one of the first people to start putting out timestamps, so I am very grateful, and I'm glad to see Akash here again. I hope you're doing well, Akash. So yeah, thank you, and I hope you're doing great. And let's have more questions. You always have great questions. So the question is, under Brane Cosmology, how much do you think the Ekpyrotic universe makes sense? Is it supported by mathematics? So I essentially have to explain two things here. What is Brane Cosmology and what is the Ekpyrotic universe? So settle down and let me tell you the story. So what's Brane Cosmology? First of all, let's talk about Brane Cosmology. So Brane Cosmology is a theoretical framework in theoretical physics that extends the concept of extra dimensions. So what are dimensions? We know the three dimensions: length, breadth, height. And we also speak about the fourth dimension, time. So in general relativity, we have four-dimensional space-time. Okay, so these four dimensions are the familiar dimensions for us. So in Brane Cosmology, we extend this concept. We extend the concept of dimensions beyond the familiar 3 plus 1 4 dimensional fabric that we kind of understand. And you can have more dimensions, 5 dimensions, you could have 10 dimensions, 11 dimensions, 26 dimensions, and so on. So all this is part of string theory and M theory. And yeah, main concept is more than 4 dimensions. So Brane Cosmology, so the key concept here is a brane, and obviously you have bulk also. Let me explain what is brane, what is bulk. So the term brane is short for membrane. So in this concept, you have multi-dimensional objects within a higher dimensional space. Let's say you have 5 dimensional space, or you have 10 or 11 dimensional space. In that, you have a brane which is, let's say, 3 dimensional. Let's talk about two branes. A two brane is a 2 dimensional surface. A three brane is a 3 dimensional volume. A four brane would be a 4 dimensional hypervolume, and so on, within a much larger thing called a bulk. Okay, so yeah, so a brane is short for a membrane. It is a multi-dimensional object embedded within a higher dimensional space or space time. Okay, so the observable universe in Brane Cosmology is typically thought of as a 3 dimensional brane embedded in a higher dimensional hypersurface or hypervolume, which is called the bulk. And where are these extra dimensions, you say? So these extra dimensions could be compactified such that we cannot observe them, or they could be large also, but for some reason we don't observe them. But the more popular way of looking at it is that these dimensions are so small, so tiny, so curled up and compactified that it's not possible for us to observe them. But their effects uh, are very much significant. Okay, and the bulk is this higher dimensional hypersurface, hyper volume, whatever, hyper volume, hyperspace, whatever you want to call it, within which brains exist. So that is the bulk. So brains live inside the bulk, and the bulk can have its own properties, it can have its own dynamics, its own rules, and all of these obviously will influence the brains. So now let's talk about forces. We know that we have these forces in the universe. We can think of, we can, how many forces do we have? Four, right? What do we have? Electromagnetism, gravitation, the weak force, and the strong force. The four forces that we know of. Now, um, one of the interesting things in brain cosmology is how these forces operate. So in brain cosmology, the standard force like electromagnetism, the strong force, the weak force, these three forces, they operate on the brain only. They are confined to the brain, whereas gravity propagates into the bulk. Okay, so let me repeat that. Electromagnetism, the strong nuclear force, and the weak nuclear force are confined to the brain only, to the three dimensions that we are familiar with. But gravity propagates into the bulk, which means it operates on all the dimensions. Let's say you have 5-dimensional hyper volume or whatever hyperspace, or you have 10-dimensional, 11-dimensional hyperspace. Then gravity operates on all of those dimensions, and that explains why gravity is much weaker compared to the other forces, because it leaks out into all these other dimensions. So that's how this theory, brain theory, explains why gravity is weak. I mean, that's the hierarchy problem. Why is gravitation? Why is the force of gravity exponentially weaker than the other fundamental forces? Exponential is a weak word. That's how much weaker gravity is compared to even the weak nuclear force. Okay, so that's called the hierarchy problem. And by allowing gravity to spread across and leak into all these extra dimensions, it naturally weakens its observable strength on the three dimensions that we are familiar with. Okay, so that kind of explains the hierarchy problem. And then there are various models in brain cosmology that explain the origin and evolution of the universe. For so there is a model called the Raman Sundaram and uh, Lisa Randall and Raman Sundaram. The Randall Sundaram model. So according to the Randall Sundaram model, the universe that we live in is a three brain, because it's three dimensions, which lives inside a 5-dimensional bulk. And that kind of explains certain cosmological observations. Uh, and brain cosmology can provide explanations for the Big Bang and cosmic inflation. For example, it suggests that, let's say, you have this hyper space which contains multiple brains, and this some models that suggest that the Big Bang was actually a collision between two brains. Okay, so the Big Bang was, it actually posits an origin of the Big Bang and what came before the Big Bang. So you have two brains and they collide within the hyperspace. And this collision releases tremendous amounts of energy, which causes the effects that we are familiar with as the Big Bang. So if you want to visualize brain cosmology, you can imagine a sheet of paper, which represents our three-dimensional universe, a three brain, and this sheet is floating in space that we are familiar with, which is actually the higher dimensional hyperspace, the bulk. And there could be other sheets of paper parallel to ours or in other parts of the hyperspace. And the bulk itself, the hyperspace, could be gigantic, vast, and complex, that beyond our imagination. Okay, so objects and forces on the sheet of paper are confined to the sheet, but gravity, it leaks out and goes into the hyper dimensional bulk. That is kind of how brain cosmology works. Now, what is the Ekpyrotic universe? So the Ekpyrotic universe is a cosmological model that proposes an alternative to the standard Big Bang theory, and it's based on ideas of string theory and brain cosmology. So it suggests, like I said, that the universe was created not from the Big Bang, which happened for no reason, but it was the result of a collision between two brains. And the word ekpyrotic comes from Greek pyrosis, pyrite. Okay, it's something to do with fire. Okay, so what are the what are the key concepts of the ekpyrotic inflation universe? So there was a brane collision. Okay, the universe exists. The universe that we live in exists in a three-dimensional brane. The birth and evolution of the universe were the result of a collision between our brain and a different brain, another brain that exists in this bulk. And this collision released gigantic, vast amounts of energy, which triggered the creation and expansion of the universe. Okay, so there is a pre-Big Bang scenario in this. Okay, so according to Big Bang cosmology, it all starts with a singularity or something close to a singularity. But the ekpyrotic model, it says that there was a pre-existing state, and that's the difference. And it avoids certain it avoids the singularities and infinite densities, infinite curvature, infinite temperatures, all that which come along with the Big Bang cosmology, right? So that is what the ekpyrotic universe thing is. And the ekpyrotic model also suggests that the universe could undergo an endless cycle of these brain collisions, expansions, even contractions. So let's say you have brains that collide periodically, right? So it's kind of a cyclic process. So each collision is a new Big Bang. Then you have an expansion. Then you have a cooling, eventual contraction, let's say, and then there's another collision which does the same thing again. So yeah, that's the ekpyrotic universe, and you can visualize it as two parallel sheets of paper in a higher dimensional space, and they are moving towards each other and they collide, and that initiates the Big Bang. Now you're asking about mathematics, right? Is the ekpyrotic universe supported by mathematics? So yes, it's obviously built on equations, mathematical equations derived from general relativity, from string theory, and brain dynamics. And these equations describe how the brains evolve and how they interact, how they collide within higher dimensional space. And it uses various modifications of the Einstein field equations to incorporate the extra dimensions and brain interactions and all that. So yeah, so that's brain cosmology, and it needs to match observational data, and it predicts certain effects. It predicts the formation of large scale structures like galaxies and clusters of galaxies through the growth of initial density fluctuations, which we spoke about in the previous answer also. It predicts the presence of baryon acoustic oscillations, which are regular periodic fluctuations in the density of baryonic matter, visible baryonic matter, which is the all the matter that produces light in the universe. So it predicts the presence of regular periodic fluctuations in the density of this visible baryonic matter, and so on. So it makes some predictions, some of which are actually bore out, and there are some large scale uh, structure surveys coming up. For example, the Euclid satellite went up into the L2 Lagrange point recently, I think last year. And it's going to start operating very soon if it's not already operational. And there is an observatory coming up in Chile called the Vera Rubin Observatory. So data from all these experiments will be used to will be used to test more of these predictions of the ekpyrotic model and other models as well about density fluctuations and higher order statistics and whatnot. So that is the long-winded answer to this question. That's what brain cosmology is. That is what the ekpyrotic universe is. That is how it is supported definitely by mathematics. Very robust, very interesting, very complicated mathematics for sure. Yeah, it makes predictions that actually can be tested, that can be falsified. It's falsifiable predictions. So it's a good model for sure. And let's see how it is borne out by upcoming experiments and tests. All right, great question. Okay, Indrajit says, recently I came across a paper about the confirmation of gravitational wave background existing in the fabric of space. India has also given its contribution in the international research by measuring millisecond pulsars in this experiment called Pulsar Timing Array. How does this all work? As these ultra low frequency gravitational waves are hard to detect. Okay. I haven't seen a paper that confirms the gravitational wave background, which would be it would be startling if that happens, and nobody would be happier than me. So, what is this gravitational wave background? We are quite familiar, hopefully, those of us who are interested in physics, with the cosmic microwave background, right? Which is the leftover light of the Big Bang. the cosmic dawn, right? That's what it is. Now, what is the gravitational wave background? So the early universe also produced gravitational waves, tremendous numbers of tremendous amounts of gravitational waves, and that should also be there in the background. Now, what are the things that can produce gravitational waves? First of all, cosmic inflation and the things that happen within cosmic inflation, that obviously can produce gravitational waves. uh, Primordial black holes and their interactions can produce gravitational waves. In today's universe, the merger of black holes, the merger of neutron stars, the mergers of neutron stars and black holes, and various such cataclysmic events can produce gravitational waves. um, so you will have, and we know that gravitational wave exists. These waves exist by now. We know that the first detection was in 2015, if I'm not mistaken, by LIGO. So we know these waves exist, but right now the technology that we have, it is such that we can only measure not waves but tsunamis. I'm talking about amplitude. See, waves come in various sizes, right? You've got tiny ripples, you've got gigantic waves, tsunamis. So right now we can only observe gravitational wave tsunamis. But I assure you, there's a gravitational wave background out there with medium-sized waves, small waves, and then those tiny little ripples in space-time. And when we start detecting that, those ripples and those smaller waves, that's when we're gonna end up having a new set of eyes that will help us see the universe in a light that we've never seen. It's not light; it's gravitational waves. So we are familiar with the light, right? The light that we are familiar with, that is also waves, but it is electromagnetic waves. And similarly, there are gravitational waves, and we don't have eyes that can see gravitational radiation, but those waves do exist. We know that. So that is what the gravitational wave background is, and it exists in the fabric of space. It's everywhere, but we don't. It's too faint because, like we just discussed, the gravitational force is the weakest of the force. It is exponentially, hyper exponentially weaker than the closest weak force, which is the weak nuclear force. And that's why these ripples are so insanely hard to detect. Essentially, you would need to have a detector the size of the Milky Way to, to detect some of these effects and so on. Uh, so that's what it is. So I haven't seen any evidence of the confirmation of the gravitational wave background. I know it's there. We all know it's there, but the confirmation, no, it's not happened as far as I know. But I will look it up. I mean, I know the technology doesn't exist to confirm this. Okay. Now the other question is about millisecond pulsars and the pulsar timing array. How does this work? Uh, Ultra low frequency gravitational waves are hard to detect. All gravitational waves are hard to detect. Now, what are millisecond pulsars? What is this thing called the pulsar timing array? First of all, what's a pulsar? So a pulsar is a highly magnetized neutron star. What's a neutron star? A neutron star is a gigantic atomic nucleus. Just neutrons. Neutrons, that's it. It's a gigantic atomic nucleus. It's the size of a small town or something, but it is the mass of an entire star essentially inside it. And I'll not go into the way these objects are produced, but yes, you have neutron stars. Now, some of these neutron stars are extraordinarily highly magnetized. Okay. And they spin at a very high rate. And this magnetization of this property, that it's highly magnetized, it ends up uh, doing something strange. The neutron star emits beams of highly energetic radiation, electromagnetic radiation, which is light, and whatever other forms of radiation in whichever frequencies, X-rays, gamma rays, whatever you want to call it. Yeah. So it emits two beams of highly energetic radiation in opposite directions, and it spins around its axis very rapidly. So that's a pulsar. Now, what's a millisecond pulsar? A millisecond pulsar is a pulsar whose period of rotation is less than 10 milliseconds. Okay? Less than 10 milliseconds. So that's a millisecond pulsar. And we can detect pulsars on Earth. I mean, some of them, their beams of radiation are pointed towards Earth. So we get these, and these are extremely highly periodic, beep, 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 but at a millisecond rate. Okay, you get that. And it's extremely precise. The timing is incredibly precise. Okay, these millisecond pulsars. So now that's what a millisecond pulsar is. Now, what's a pulsar timing array? So we have millisecond pulsars. We know a bunch of known such pulsars. And what we can do is we can have an experiment in which we detect an entire the pulses from an entire array of pulsars. Okay. Now what that does is that if there is a gravitational wave that comes through, that passes by, then there's going to be a very tiny discrepancy in the timing with which the pulse reaches you. And if this happens with multiple pulsars at the same time, and we know how it is correlated, then we know that we have detected a gravitational wave. And based on the anomaly, based on the discrepancy, we can actually determine the characteristics, certain characteristics of the gravitational wave. So that is the principle behind a pulsar timing array. And we have such experiments out there at work. Thus far, they have not detected gravitational waves. Thus far, all right. Maybe because our instrumentation and our the accuracy with which we make these detections isn't strong enough. Maybe it's not accurate enough. So there are reasons for this, multiple reasons that we can think of, and very plausible reasons. But thus far, we have not detected gravitational waves using a pulsar timing array. So that's what I know. I'm not sure about India's contribution in this. I have not read about that, and I have not read about the confirmation of a gravitational wave background. But I hope I have explained the concepts. What is the gravitational wave background? I've explained, hopefully. What is a pulsar? What's a neutron star? What's a millisecond pulsar? And what's a pulsar timing array? And how does it? How do such experiments, hopefully in the future, detect gravitational waves? So, yeah, there you have it. Okay, Pranav Hariharan says in quantum mechanics, we start by reading about matter waves or the de Broglie or de Broglie, like we say, the de Broglie hypothesis. So my doubt here is that what exactly is oscillating in a matter wave? Yeah, matter waves, right? So what is oscillating? In electromagnetic waves, we know that you have electric and magnetic fields that are oscillating. Yeah, that way, that way. Yeah. So we in electromagnetic waves, electric and magnetic fields are oscillating. Yes. In gravitational waves, what is oscillating? So we're not talking about gravitational waves here. We're talking about the Broglie waves. Okay, matter waves. We not don't let's not confuse that with gravitational wave. That's a whole different thing. In gravitational waves, it's space time itself that is distorted, but we are talking about matter waves here. So let's talk about that. So what is the de Broglie hypothesis, which is better known as wave particle duality? It is something Mr. No, Prince Louis Victor, whatever the Broglie, he was a prince. He proposed this as a massive breakthrough in the 1920s. It was a massive breakthrough in quantum mechanics, in quantum physics at the time. We did not have mechanics yet. It was a bunch of jumbled, disparate experiments, and it was very, very confounding until uh, Mr. Paul Dirac came in, and Mr. Heisenberg came in, and Schrödinger came in, and Pauli, all that. Okay, I'll not go into the history of this. So the hypothesis, the Broglie hypothesis, is that particles like electrons, etc., have a wavelength. What is this wavelength? It is h divided by p, where h is the Planck constant and p is the momentum of the electron. Okay, and this wavelength of the electron or whichever particle, fundamental particle, subatomic particle, it's associated with the wave-like nature of the particle. And then you have the concept of the wave function. So this wave-like nature of the particle is described by what we call a wave function. So that is the wave particle duality. Particles have a wave character, a wave nature, and waves also have a particle character. I mean, talk about the photon. The photon is a particle. When we talk about when it comes to certain phenomena like the photoelectric effect, you cannot explain that unless you consider light to be a particle, a photon. Yes, but when it comes to other things like the double slit experiment, etc., you have to think of light as waves. So there, and that applies to electrons as well, the same wave particle duality. So a particle, so you can have a particle, everything has a particle as well as a wave nature. That's the wave particle duality. Now in quantum mechanics, the state of a particle is described by what we call a wave function, psi. Psi. So what is this wave function? This wave function is a complex valued function of space and time, of x and t. And this wave function contains all the information about that one particle. So that one particle, let's say this electron that we are referring to, has a wave function. And this wave function is a function of position and time, space and time, x and t. And this wave function contains all the information about the particle. And how do we actually utilize it? We take the square of the absolute value of the wave function. It's a complex valued function. So we take the square of the absolute value of the wave function, and that gives us what? It gives us the probability density of finding the particle at a position x at a time t. So psi, this wave function psi, is not directly observable. It has no real physical meaning. The square of its absolute value has a physical meaning, and that is a probability density. So there was, when the wave function first came up, okay, when Schrodinger came up with the Schrodinger equation, there was this big debate, and everyone was perplexed as to what does this psi, this function psi, describe. And Schrodinger was of the opinion that it describes the distribution of the electric of the charge of the electron over space. That was what he believed initially, until, well, there was a revision of the understanding of this. So psi itself, the wave function, is not observable. Only the square of the absolute value of the wave function, it has a physical meaning. It is a probability density. So now the question is, what is oscillating, right? What exactly is oscillating in a matter wave? So it's not a physical oscillation. Okay, the de Broglie waves, or which are described by the wave function psi, they are not like classical waves. In a classical wave, in a wave of water, you have a physical quantity. Like, let's talk about the light. So you have the electric field which oscillates, right? Or in sound waves, you have pressure that oscillates, and so on. But in matter waves, it is the probability amplitude that exhibits wave-like behavior. That's what it is. So this oscillation is in the mathematical sense of the complex phase. It is not a tangible physical quantity that we're talking about. Okay, so in a matter wave, it's the complex phase of the wave function that is oscillating, and this oscillation is not a physical movement of matter, but a variation in the probability amplitude described by the wave function. And you if you really want to understand this, I mean, there's no intuitive way of looking at it, right? Because quantum mechanics is completely non-intuitive. It doesn't make any sense whatsoever. You just have to get used to it. You to get used to these ideas. You cannot give metaphors and examples of the real world, even though the real world emerges from the quantum world. Okay, so that's what it is. That is what matter waves are. That is what the Broglie. It's not a hypothesis. It's the wave-particle duality, and that's what it means. Okay. Feminist Slayer says, why the primary focus on reducing carbon dioxide emissions when there are other potent greenhouse gases like methane and nitrogen oxides? Are there efforts to reduce these other gases as well? Additionally, while promoting solar energy to meet our energy needs, how are we addressing the issue of e-waste generated from solar technology? Lastly, does the extraction of fossil fuels and minerals from the earth increase the risk of natural disasters such as earthquakes? Okay, multiple questions in one, but it's a good question. Yeah, we talk about reducing carbon dioxide emissions. There are other greenhouse gases, potent greenhouse gases like methane, which is again something that it's a hydrocarbon. Methane is what, CH4? If I know chemistry, I'm not that great at chemistry. Okay, I think it's CH4, methane. Okay, it has carbon, right? And then you have nitrogen oxides and all. But the major bulk of the greenhouse gases is carbon-based compounds like carbon dioxide and methane and so on. Yeah, but we talk about carbon dioxide. How much carbon dioxide? Because the bulk is carbon dioxide. Are there efforts to reduce these other gases as well? I'm not sure. Right now, we are focusing on carbon dioxide because it is the biggest problem that we have. Right? So yeah, because carbon dioxide is the major greenhouse gas, and it is what is emitted. Let's say you burn coal, what comes out of it is carbon dioxide that mostly comes out. There are other gases also that come out, but the major gas that comes out as a byproduct of burning of coal is carbon dioxide. Once again, when you're combusting petrol, gasoline, kerosene, which is aviation fuel, or whatever other hydrocarbon petrochemical thing, the major byproduct of this is carbon dioxide. So it makes sense to talk in terms of carbon dioxide. Yeah, but of course, there are other greenhouse gases. When it comes to animal agriculture, there's the emission of methane, which is a big thing, and so on. But we focus on carbon dioxide because it is the major component of the greenhouse gases and the greenhouse effect. Now, talking about solar energy to meet our energy needs, of course, there's going to be e waste generated from solar technology. So, let's say you have a solar panel, and a solar panel has a certain lifespan. Okay, it's going to have a certain time in which it is useful. It has a certain limited amount of utility. Let's say 5 years, 10 years, let's say hypothetically. Okay, after which it will no longer generate the amount of power that you need. So you're going to have to dispose of it and get a new one, right? So what happens to the thing that you dispose, the solar panel that you dispose? It's going to go into waste, and it's going to get hopefully recycled, or it just goes into a landfill, or what, I don't know, whatever happens. So that is the electronic waste, the e-waste that you're referring to over here. And obviously that's a problem. But the deal is this: all human activity produces waste. You just can't do a thing about it. Every biological activity produces waste, by the way. I'm sure you're aware of this. And biological activity on a large scale can transform the planet. What was the great oxygenation catastrophe? It was one of the first extinction events. I mean, before that, before this thing happened, the Earth was a very different place. The atmosphere was very different. There was no oxygen. It was for us a hellish place, a whole combination of highly noxious gases from our perspective. And then these microorganisms evolved, unicellular organisms that gave out a tremendous amount of oxygenation. And this oxygen was a poison for all other organisms, and it killed off most of them. There was one of the first extinction events, the great oxygenation catastrophe. And even today, oxygen in high concentrations and all that is poisonous for even us. So biological activity can produce waste that can transform the planet in a let's say deleterious fashion, right? So there is that. Then why do we have so much iron rust, iron ore? Where does iron ore come from? It comes from bacterial activity again, deep in the earth's antiquity. And when it comes to human activity, we need to extract resources from the environment. Even during the Stone Age, we used stones as resources. So we were, because our population was so low at the time, it did not have any real effect on the planet. But let's talk about a time about 5,000 years ago, when you have the Saraswati Sindhu phase of the Indian history, Indian civilization, in which the population of that region, northern and western India, was about 5 million. At that time, to sustain that population, obviously you would need to extract resources from the environment, the ecosystem, the ground. You would have to do mining, and also obviously that will have some effect. Obviously, a 5 million human being population isn't great compared to what it is today, what, 7, 8 billion? And India's population is 1.4 billion. Now we're talking about genuine earth changing consequences. The point is, all human activity is going to create waste. It's going to affect the planet in some way or the other. And it's going to change the balance of the ecosystem, of the environment in some way or the other. So we do need transportation, we do need energy, we do need all that, and it all has to come from somewhere. Now, ideally, you want to have a clean source of energy. So even if you want to have a clean source of energy, like solar energy, you're gonna need to have these solar panels, and those solar panels eventually will generate waste. Or you could go for nuclear energy, but then it will produce nuclear waste, which is essentially just thermal stuff which you can dispose of safely. But yeah, that's a thing. So yeah, there's nothing you can do about it, no matter how much you optimize the technology and how much you try to reduce the impact on the planet. It's going to have an impact. And the last question is, does the extraction of fossil fuels and minerals from the earth increase the risk of natural disasters such as earthquakes? Well, if you have a reservoir of petroleum that you completely empty, it's going to cause a void below the earth's surface, and that can obviously cause the displacement of soil and rock and whatever, and it can cause a minor localized earthquake. And more than that, it's actually damming up of water that causes natural disasters such as earthquakes. If you have a region that is of the planet that is hilly, lots of rivers, and you dam up like 50 of those rivers in a reasonably small area, then that can cause earthquakes and things like that, natural disasters, or it can cause flooding and so on. So yeah, it's not the extraction of fossil fuels and minerals from the earth, but it's damming up of water of rivers, etc., that has a higher chance of causing earthquakes and so on. But even the extraction of fossil fuels, petroleum, raw petroleum, if you completely empty out reservoirs, then it can cause the collapse of the reservoir because it leaves a void behind, and then it can perhaps cause an earthquake. So yeah, there we have it. Okay, Swapnil says, are there any non-human living organisms, such as plants or animals or insects or microorganisms, that exhibit suicidal tendencies or engage in self-destructive behavior, leading to their own death? Right. There are cases in which this happens. It's more of, who was it? Altruistic suicide. Somebody said, I forget the name of the sociologist who came up with altruistic suicide. I am sure some of our viewers will know who it was. Anyway, so let's talk about a colony of ants. A colony of ants, when it comes under attack by a predator, let's say a wasp or a hornet or something, then in certain species of ant, the ants can the worker ants can self-destruct and release some sticky chemicals or some noxious chemicals that ward off the attacker, the predator. So they do it, they destroy their body and die, essentially commit suicide for an altruistic purpose, to protect the hive, the ant hill or ant hive, and to protect the queen. Similarly, among bees and hornets, etc., I am sure there is similar behavior also. Worker bees, drones, etc., they in some species they exhibit some such tendencies. Then when it comes to animals like the octopus, so when an octopus lays eggs, it stops eating, and its entire duty once it has laid the eggs is to protect those eggs in certain species of octopus. And they stop eating, they stop doing anything for themselves, and they just watch over the eggs until the eggs hatch, and then they die. So that is the kind of biological evolution it is, that your sole purpose is to eat and grow and get large to a certain size, attain maturity, uh, mate, reproduce, lay your eggs, and then watch over those eggs until they hatch, and then you die. And then the same process continues over again in the next generation of octopi. So that is what you have in octopuses or octopi. And then there is the what else do we have? I think that there was this myth that lemmings commit suicide. The lemmings are a species of rodent that is found in the far northern regions, in the Arctic Circle and so on. So these rodents, they migrate in large numbers, and sometimes they end up in the wrong place and they can fall off hills. So it looks like, and because there is this herd behavior, sheep like behavior, they don't see what's far away, they just see what the guy in front of you is doing. And that's why if he's falling off the cliff and everyone's pressing from behind, you end up falling off a cliff. So they don't do this intentionally, but sometimes it's been seen to happen, apparently, that lemmings in large numbers fall off a cliff and fall into the ocean, or fall from a large height, and most of them die. So, but it's not a suicidal behavior, it's just something that happens by accident. Then you have certain aquatic animals, like like dolphins, like porpoises, like whales, cetaceans, that beach themselves. Now, beaching is not understood very well. Why do certain whales, why do certain dolphins, etc., beach themselves? So these animals, whales and dolphins, these are actually animals, they're not fish. They have lungs, they breathe like us. They have to rise to the surface every so often, take a deep breath of air, and then go and do whatever business they conduct under the water surface, but they have to rise up periodically to breathe. So if one of these animals becomes beached on a beach away from the water, it won't lead to their death immediately because they have lungs and they can just survive out of the water. But what happens is that their skin, it once it comes in contact with the air for an extended period of time, and when there's sunlight, it kind of dries out very rapidly, and then that causes their terrible slow death. That's what happens. And in the case of large whales, if you are beached, then their body mass is so large that it eventually squashes their organs in their lungs, and they die a terrible death. So I'm not sure if it is very well understood why these animals sometimes beach themselves in very large numbers. Maybe it is just accidental, something that happens accidentally. Maybe they're migrating and maybe they come too close to the shore and then there's a tide or whatever. I'm not sure what happens, but you could say it is suicidal behavior because it ends in their deaths. So yeah, there are many examples of animals that do exhibit such tendencies and behaviors. In the case of insects, etc., it is an altruistic suicide. They give up their lives in order to safeguard the hive or the community, and especially the queen. In octopuses, it's about ensuring the survival of your offspring, of your descendants, so spreading of your genes. And in the case of whales, etc., it's not understood why they beach themselves. But yeah, there are, like I just say, there are multiple examples of such behavior. Okay, Ritik Pawar says, how would the world change if OpenAI or Google created AGI, artificial general intelligence, today, making them more powerful than governments? What would be the impact on industries, the economy, and society? Well, if, let's say, a private company, is able to create AGI, artificial general intelligence, which means they have an AI system that actually becomes self-conscious, not even not even self-aware, but it can essentially do everything a human being can do, but much better at a larger scale. So that's artificial general intelligence. So it can understand the spoken word, it can understand music, it can understand everything we can understand, but at a higher level. That's artificial general intelligence, and it does not necessarily have to be self-aware. So what happens if this is created? What happens if Google creates or OpenAI creates this? That would definitely make that entity, that company, more powerful than governments. Obviously, it's not really the power of a government because that company doesn't have nuclear weapons. It doesn't have an army to unleash on anybody. It doesn't have an army of bureaucrats and police at their beck and call. It doesn't have any of that. But it has the AGI that can be tremendously, insanely powerful in the right or the wrong hands. So what happens if this scenario unfolds? I'll tell you what happens. Uh, First of all, the moment this happens, the government, the parent government, which is the US, will essentially take over this thing. We will not know that they've taken over. First of all, they will not announce this to the public. This is not supposed to be announced to the public because that godlike capability should be secret. And then they will take full, they'll make full use of that in extending the amount of their power. So it would be the government and the military that actually acquires the technology, keeps it secret, and leverages it to the fullest of its potential. That's what it would do. And of course, that would lead to a complete American dominance. If you don't already have it, it would lead to the complete dominance of that country on all the industries of the entire global economy and the global society. So it will be a tremendous. See, technology is a force multiplier. The first technology was the stick and the stone. So if you could punch somebody, a stick would impart way more power than that. And if you could punch someone, now you could throw a stone with the same amount of force, but it's a harder object. It can crack someone's skull. So that's a force multiplier. Then you have bows and arrows, which again, it's a force multiplier. Then you have machine guns and so on. So technology is a force multiplier. And such abstract technology like AGI is a tremendous force multiplier. When you couple it with robotics, when you couple it with the smart warfare, with drones and whatnot, It makes it tremendously powerful. And when you use it for surveillance, I mean, we've heard of the PRISM program that Edward Snowden spoke about more than a decade ago. Imagine what they have today, but with just the non-AGI artificial intelligence technologies. And with AGI, it just becomes impossible to beat once you have it. So yeah, that's what it would do. So it would lead to the complete monopolization of everything by the entity that owns it, and that is not that is a very scary thought, which means the rest of the world now has no chance of anything anymore. And they would obviously actively try and prevent any other nation or any other entity from developing similar capabilities. So yeah. Okay, a couple of questions together. So Curious Prabhat says, do you think we can see an AI like Skynet, Terminator movies, which can be a threat to us in a few years from now, as the advancements in this sector are very rapid? And the second question is, I've been watching many sci-fi movies with robots, such as industrial, medical, military, and humanoid robots. When do you think it will be possible to have these types of robots with how AI is advancing very quickly? I remember Elon Musk had unveiled a humanoid robot back in 2022. The dangers of AI and robots are concerning, and what do you believe is the best way to prevent such a scenario, such as Terminator? What are your thoughts on creating humanoid robots that look identically to humans in the future, such as Sophia, even though we can tell she's a robot? Okay, a lot of stuff to unpack, but it's about the threat, the dangers of AI when you combine that with robotics. When we talk about the Terminator movie, it wasn't the AI that was dangerous; it was the robots that were dangerous. And those robots were dangerous because they were AI-equipped robots, right? And obviously, they could travel through time, which is like, ooh. So that is something we don't need to worry about. That won't happen anytime soon. Uh, so those robots, first of all, were kind of indestructible because they have a metal endoskeleton, right? And they were artificially intelligent, which means they were autonomous, but they had a clear sense of purpose. And they were obviously commanded and controlled by a central intelligence, and they were programmed with a very clear set of objectives. So that is what made them dangerous. And obviously, the real danger was that they sought to take control of the planet and to enslave humanity. And the nuclear war was kind of the issue, right, in the Terminator movies. So could this happen? So look, today we don't have such advanced robots, but obviously AI, with a sufficiently powerful AI, we could develop robots that capable. So in recent years, you see companies like Boston Dynamics, which have been struggling for so many years to develop good robots. Nowadays, they have robots that can dance and do acrobatics and whatnot. And you have these robot dogs that can do terrifying things like shoot weapons at people, machine guns and whatnot. So we're getting there. We're getting there. Soon you will have robot soldiers, an army of, let's say, 10,000 robot soldiers and another 10,000 robot dogs. Imagine that bearing down on you. So no matter how brave your soldiers are, how valorous they are, how do you beat that? So yeah, we are very close to that actually. But in the Terminator movie, the robots were controlled by a central artificial intelligence. Was it self-aware? I'm sure it was self-aware. Yeah, it had become self-aware, and it had its own agenda. It was not controlled by any government or any person. It had its own agenda to rid the planet of humans. I believe that was the agenda, something like that. So right now we are not in that scenario where an artificial intelligence, as far as we know, has become self-aware and has gone rogue, so to say. Um, so yeah, so right now the AIs that we know of are controlled by either corporations or governments, and those corporations, um, they are in the control of the governments. So that's where we are right now. Robots. So yeah, that's all of that. Elon Musk had unveiled a humanoid robot. Yeah, sure. Boston Dynamics has unveiled really capable robots. Now about Sophia, I'm not sure what the Sophia thing is. I think it's a robot that was unveiled in Hong Kong or something, which looks kind of human-like, but you can tell that it's a robot because it's still not, well, it's still quite apparent. But eventually we will have more and more humanoid robots that look more and more like humans. But the real deal is when it becomes Terminator like, which means you have living tissue over a metallic or an artificial endoskeleton. That's when you won't be able to distinguish between humans and robots, if that ever happens. Um, so that could be further away. Obviously, grafting living tissue, human-looking living tissue on a robot, that is right now it's completely science fiction. We are nowhere close to that. If such technology existed, it would be used for regenerating people's limbs and all that. Or some people need face transplants. You could do that with their own DNA so that it's a natural looking face, and so on. So we are still very far away from those technologies. But yeah, AI and robotics, the combination is scary. It's super scary. In AI, the way it's progressing, yeah, you could have very powerful, very dangerous robots very soon. The only thing is that AI, as far as we know, as far as we are aware, isn't self-aware, and it doesn't have an agenda of its own. So it all depends on the agenda of the controlling entity, which is either the corporation or the government. And we're talking about the US mainly, and also the Chinese also have their own AI systems apparently, and so on. Yeah. So yeah, that's what. Let's take a few more questions. Harshil Agarwal says, "Why are why oceans deep inside are cold, but as we go deeper inland, it becomes hot?" That's a great question. Now, why don't teachers allow kids to ask such questions? It's a very fundamental question. Looks very simple, but it's a great question, right? So let's say you are on the surface of the ocean in a boat. Let's say at the equator. At the equator. At the equator, if you put your fingers in the water, if you dip your feet in the water, it's going to be warm water, nice and warm. Okay, at the equator. But let's say you dive under the water with equipment. Obviously, the deeper you dive, the colder the water gets. You go a kilometer down, it's going to be much colder. You go even way further down, it's going to get colder and colder. Of course, there's a limit to which it can become cold, but the main thing is, as you go deeper inside, under the ocean, it gets colder. And there is something called the thermocline, and so on. I will not talk about that. So that is what we know. As you go deeper under the ocean, under the water, it gets colder, even in lakes. But as you go deeper underground, it gets warmer and hotter and hotter. Why is it so? So it all depends on what is the source of the heat. What's the source of heat when it comes to oceans and lakes? And what's the source of heat when it comes to going underground? Big difference there. When it comes to oceans, the source of heat is the sunlight, the sun. Okay? So the maximum sunlight is at the equator, which is why oceans are really warm at the equator. You go to the polar regions, there is much less sunlight there, which is why oceans are cold, and you also have icebergs and whatnot as you go in the Arctic Circle and all that. Okay, so the source of warmth, of heat for oceans, for water, is sunlight. There is no other source of heat. And obviously, you have glacial melt water, you have water that continually melts from the polar regions, and some of it reforms also. And all of that is it obviously becomes part of the ocean. And the colder the water is, the deeper, the heavier it is, which means it will be found below a certain depth in the ocean. So that's why, because of these various reasons, and because of the only source of heat being the sunlight, and we have night also in the ocean. So that's why you have ocean currents and all that, and that's why you have the phenomenon that the deeper you go, the colder it gets. Okay, now when it comes to the land, the deeper you go underground, the hotter it gets. Why is that? It's because underground you have heat. What is that heat? It is the leftover heat of the formation of the solar system. And at the core of the earth, the planet, there is the core. There's an inner core and outer core. The inner core is solid nickel iron, it's believed, and the outer core is molten nickel iron that generates the magnetic field of the earth, which keeps us alive. And then if you go further beyond that, you have magma, the magma layer, and so on and so forth. Okay, you can look up an image, a Google image of the cross section of the earth. So as you go deeper underground, you have all of this, and that's why you have heat the closer you get to the magma layer and all that. And there's another source of heat as well underground, which is radioactive decay of various radioactive elements and isotopes that are found naturally in the earth's soil. So that also contributes to the heat of the Earth. And the deeper you go, the more radioactive decay cumulatively makes its presence felt. So you have all of these uh, the radioactive element plus the heat from the magma layer and the core of the Earth. All of that, it causes this phenomenon. The deeper you go under the surface of the Earth, the hotter it gets. So that's why you have this tremendous disparity. The deeper you go under the water surface, the colder it gets. But over here on land, the deeper you go under the land surface, the hotter it gets. That is what hopefully explains this matter. Okay, next question. Ubendra says, you said jet engine development is very complicated because you said we need to develop jet blades from single crystal. Yep. But we have rocket technology in ISRO and in NASA and in the Chinese space program and the French and so on. We have rocket technology. I think high temperature resistant materials are used in rockets. Yes, they are. So why can't DRDO or whichever organization it is use this same technology in jet engines? It's a great question. It's a great question. And to understand why it doesn't work and why it's not that easy, you to understand the difference between a jet engine and the rocket engine. So in a jet engine, you have this continuous environment where all the engine parts, like the turbine blades, the single crystal turbine blades, they are subjected to extremely high temperatures for extended periods of time. So the temperature can be around 2000 degrees Celsius. Okay. So you have this constant exposure. So let's say let's talk about a standard airliner. Okay. Let's say you're traveling from Delhi to London. Okay. You want to deposit some money in a bank account in London. So you have an 8 hour, let's say, flight. So for 8 hours, you have this airliner, and those turbines will keep on running. Those jet engines will be on full operation for 8 hours, and the temperatures could be 1500, 2000 degrees. So there is constant exposure for a sustained amount of time, hours and hours, to extremely high temperature gases. And this material, the jet engine material, the cover, the turbine blades, etc., especially the turbine blades, these thin turbine blades, they must maintain their mechanical properties over this long period of time at high temperatures. And it's not just these 8 hours, you're going to use it over and over again, right? So it must be able to withstand this for so long. And yeah, it's called thermal cycling. So that is what a jet engine must be able to withstand. Now let's talk about a rocket engine. The rocket engine, it faces very different conditions. It actually faces higher temperatures. Okay, the combustion chamber in a cryogenic engine or whichever rocket engine, it can reach temperatures about 3000 degrees. And the pressures are even higher in rocket engines, extremely high pressures. But here's the difference. A rocket engine operates for a short duration. Okay, a few minutes. So when it comes to jet engines, we talk about hours. When it comes to a rocket engine, a few minutes, at best 10-15 minutes. Okay, so there is that. And so when it comes to rocket engines, they must be able to withstand thermal shocks, very rapid heating and cooling because when you have a cryogenic engine, we're talking about very cold temperatures, and then it suddenly heats up to ridiculously high temperatures. So that's what it should be able to withstand. Thermal shock. A jet engine doesn't have to go through that. So rocket engines use various high temperature resistant alloys of various metals. I don't remember, rhenium, niobium, whatever it was, to do that. But jet engines can be extremely heavy. I'm sorry, rocket engines can be very large and they can be significantly heavy. I'm talking about hundreds of kilograms. Jet engines have to be light. So you can see that a jet engine is very different from a rocket engine. A jet engine has to operate repeatedly for hours and hours at a time. A rocket engine typically is disposable. Typically, you operate it once. Until SpaceX came into the picture, rocket engines were disposable. You use a rocket engine once for about a few minutes, then you dump it, and it's the end of the story. You don't have to reuse it. And rocket engines can be much larger and much heavier. And jet turbine blades are thin, thin and actually fragile. So you can see how different it is. You can create a gigantic, big, robust, massive, heavy rocket engine with a tremendous amount of thrust. It'll do the job. But when it comes to jet engines, they have to be lightweight. They have these very fragile components, the turbine blades, which have to be able to withstand tremendously high temperatures, 1500, 2000 degrees Celsius, for hours at a time, sometimes 20 hours at a time. And it goes on forever. Missions that last, I mean, every other day you have to go and do this. So it's a very different thing. And that's why it is so complicated. And that's why the technology that you have in ISRO or DRDO, which is used in rocket engines, simply cannot be transposed and used in jet engines. Very different set of conditions that these two beasts have to withstand. Very different. So that's why it's not that easy. Right? You got it? Okay. Let's take a few more questions. I'm sure I've crossed 10 by now. Okay. Balram Putin says that hypothetically, if we put the entire universe in a large container, what would be outside the container? I heard in some videos, some scientists said the human brain can only imagine things that exist in the universe. We don't know about that. But if that is true, is it possible that there are imaginary things or creatures somewhere in the universe? Well, that is speculation. I don't know. But the first question is, if we put the entire universe, okay, I'm holding this, here's the universe, I'm holding it. Okay, I take this universe and I put it in a large container. Let's say it's a box. So I take this universe and I put this universe in a box, in this container. And the question is, what will be outside the container? Well, I'll tell you what, it'll be me outside the container. Want it? Look, we can only speculate. Maybe there is the bulk of the brain world. I mean, in brain world cosmology, there's a bulk outside the brain world. The universe is part of a brain world, and the brain world is a it's a three brain in a maybe 5-dimensional or 10-dimensional or 11-dimensional bulk. So maybe that's what's outside the universe. And maybe you're putting this 3-dimensional brain inside a 4-dimensional hyperspace, which is part of an 11-dimensional, which is embedded in an even dimensional, 11-dimensional, even larger dimensional hyperspace. We don't know. We can only speculate. That's what I mean. But if I'm putting the universe in a box, then outside that box, there is me and whatever else is out there. So that's what I can say. Look, this is all speculative because we don't know what's outside the universe. We don't even know if all of these things are true. We can only rely on the data, observational data, empirical evidence that we have at hand, and that doesn't tell us anything of what may be beyond even the observable universe. The actual universe may be even larger than it actually most likely is, way, way, way larger than the observable universe. So what's beyond, we don't know. We can only speculate, and when you speculate, it's no longer science, it's philosophy or religion or whatever. So yeah, there you have it. And some scientists apparently said that the human brain can only imagine things that exist in the universe. Well, I guess the universe is so large and so vast and so mysterious and so complex that anything you can imagine with your brain, which is part of the universe, maybe it exists somewhere in the universe. Perhaps. Speculation. Pure speculation. But yeah. Okay. Harshan says, what's anti-gravity? Can it somehow exist? So it is again science fiction. There is absolutely no evidence of anything called anti-gravity. So like you have antiparticles that have the opposite quantum numbers and quantum properties and opposite charges, etc. As particles, similarly, anti-gravity could be a repulsive force similar to gravity. But have we ever observed it? We have not. So can it exist? Perhaps, possibly. But have we observed it? We have never observed it. So anti-gravity is this hypothetical force, fifth force or whatever, that could have the opposite effect of gravity. So if something falls, if you have anti-gravity, it actually falls upwards or something like that. But yeah, there's no evidence for that. Amrit Singh says, I've always wondered how space looks. Does it look exactly the same as images released by NASA, or will it look different if we see a nebula with the naked eye? Look, the way space looks, it depends on how you're looking at it, what lens you're using to look at it. If you see NASA images of space, let's say you're looking at NASA images of a spacewalk. American astronauts in orbit around the Earth, they're doing a spacewalk out of the International Space Station. If you look at, let's put up some images, right? I've not put a single image on screen today, so let's do that. Give me a second, and we're gonna take a look at this. Okay. Yes, ISS. Sorry. Okay, spacewalk. So let's take a look at a spacewalk image. So you can see the curvature of the Earth in these images, right? So you can see the Earth curved. So this is one representation of how space looks. Now, Shen Zhu spacewalk. Okay, whatever the spelling is. If you look at Chinese images, look at the Earth. It is completely flat. Do you see this? There's hardly any curvature visible. Here. So what is the deal? It depends on which lens you use. Over here, I'm not sure if this is the Chinese thing, but yeah, over here it looks curved. But in most other images, the Earth looks entirely, completely flat. I mean, look at how flat it looks in this image. So it doesn't mean that the Earth is flat, by the way. It just means that they're using a specific kind of lens. And when it comes to lenses, it all depends on the focal length and so on and so forth. When you use what are the anamorphic lenses and fisheye lenses, everything looks really curved, and the focal length also matters, and so on. So that is one example of how space looks differently depending on which kind of camera you use. And we also have these lenses over here, in our eyes. That also affects the way we look at things. What's the focal length? About 50, is it 35 mm, 50 mm, 80 mm of the human eye? I think it's 35 or 50 or something, somewhere in that range. So we see the world in a certain way, which depends entirely on the way our eyes are constructed. So you use different cameras, it's going to look differently. But we're talking about the Earth from space over here. What does space look like from space? Well, space looks inky dark, just dark black. From the Earth, when we look into space, we are looking at space through the atmosphere. And that's why it has atmospheric effects. Stars seem to twinkle. You go out there into orbit, Earth orbit, the stars won't twinkle at all. They're just dots, bright dots in space. And space itself is just ink black. That's how it looks. And it looks way larger than what we can imagine. You go out into space, it's all around you, and you're going to be shocked at the immensity of space. It's really scary. That's what I hear. I haven't been to space, by the way, so I can't tell. I'm only giving you secondhand information from what I've heard and read the astronauts saying. So yeah, that's what space looks like. All right, I've taken a whole bunch of questions. Now let me take some questions from the live chat. I'm going to take a few questions from the live chat, and that will be it. Aditya Kumar Shaw says flat earthers got evidence. Yes, the Chinese have proven the flat earthers right. They've produced pictures of the earth which is entirely flat. Outstanding. An Kurama says 35 mm for human eyes. Yes, that's right. Okay, if there are any questions, I'll take a few questions from the live chat so that there is some interactivity. What do we have? Om Kulkarni says, what do you think about the possibility of antimatter propulsion for future space travel? And what kind of restrictions does it currently face? Well, currently, antimatter is about a few $1 trillion per gram. Okay? There's only less than a gram of antimatter ever produced in various colliders, like the Large Hadron Collider and so on. Tremendously expensive to make. And very small quantities exist. In the future, if we have reasonably good amounts of antimatter, great fuel for future space travel, great fuel for energy generation. Okay? But right now, the constraint we face is that the technologies that we have are very, very primitive and rudimentary. So the restriction that we face, the constraint we face, is that our technology, which produces antimatter, is extraordinarily expensive. The Large Hadron Collider, the energy budget is that of a small country per year. And then only, even after that much energy, consuming that much energy, it produces a fraction of a gram of antimatter per year. So that is why antimatter is I don't know, hundreds of trillions of dollars per gram. That's the main constraint and restriction. It's ridiculously expensive to create, and even with all that money spent, we can create only a little bit of it. In the future, if and when the technology advances, then antimatter will be a brilliant fuel for future space travel and also for future energy generation. Okay, Mubashir Madridista says, "What are God particles and why are they so important to understand? Please explain in simple words." It's not God particles; it's the God particle, and it's not really the God particle. It was not made by any god that we know of. Okay, it's called the God particle. I think it's journalists and the media that have given this name to the Higgs boson, and the Higgs field. So in quantum field theory, it's all field. The entire universe is just fields, and the particles are merely local excitations in these fields. So the entire world that we see is just Maya, it's illusion. It's just fields and the interaction of the various fields that produce the world that we live in. Now, what is the Higgs field? The Higgs boson. The Higgs boson is the particle that is associated with the Higgs field. And it is the particle that endows other particles and other particles with mass. So whichever fields interact with the Higgs field, let's say the proton field interacts with the Higgs field, which that is what gives the proton its mass. The electron field interacts much more weakly with the Higgs field than the proton field, which is why the electrons have much smaller mass than protons. The neutron field interacts with the Higgs field approximately at the same strength that the proton field does, which is why neutrons and protons have approximately very similar masses. And some fields don't interact with the Higgs field at all, which is why those particles associated with those fields have no mass. Okay? So that's kind of how I can explain this in simple words. The Higgs boson, and the Higgs field are what endows the universe with mass. But some particles and fields and their associated fields don't interact with the Higgs field, which is why those are massless. Okay? And that is what these journalists, etc., have called the God particle. It's the last major fundamental particle to be discovered. It was discovered a few years ago, and that's the one good thing the Large Hadron Collider has produced. Shrestha Mudgil says, thoughts on Terrance Howard. The great actor, I believe. He was part of a Nobel Prize, Oscar-winning movie, Crash or something, which was a very boring movie from my perspective. I saw it when I was there in the US. So good actor for sure. He's recently made some very interesting statements. I haven't seen the Joe Rogan podcast episode in which he appeared. He apparently says 1 times 1 is not 1, it's 2 or something. Look, it's fine. I think it's a good thing. I'm sure the statements he has made are ridiculous from a scientific perspective, but he's not a scientist. And what he has achieved, either knowingly or unknowingly, is that he's brought a lot of interest among the common people when it comes to science. They are now interested in science. That's good. So kudos to Terrance Howard. I have absolutely nothing against him, and I have no issue with whatever he has said. He's not a scientist, so you don't have to take it seriously compared to if a scientist were to make such statements like 1 times 1 is 3 or whatever. So he's done wittingly or unwittingly a great job in popularizing science and bringing people towards science, making people interested in science. So good job, sir. Good job. Okay, let's take maybe 1 or 2 more questions. Rampada Mahato says, Rate Khan Academy is an educational platform. I haven't used it, so I don't know, but I hear it's good. People say it's great. Salman Khan, right? The guy. I hear it's great. I haven't used it myself, so I can't rate it personally, but probably very good. Okay. Devendra Raghav says, do we have any gravitational anomalies discovered on Earth, just like seen in the movie Interstellar? Um, what was that anomaly they were talking about? Yeah, I don't know what it was. The guy, the hero, he falls into a black hole, Ginormica or something. No, Gargantua, and it is a tesseract, which is a four-dimensional thing, and he somehow reconnects with his daughter on Earth. Yeah, that did not make sense. Before that, it was all good, but it's a great movie, great movie. Now, I don't know. I could not understand the nature of the gravitational anomaly, so I don't know what it was. What is the physics behind it? Okay, I mean, when I say I could not understand what it was, I mean I could not understand the physics behind that gravitational anomaly. It doesn't work that way. That's not how gravitation works. So, yeah, the answer is we don't have any such anomalies that we know of on Earth, like in that movie, right? All right. Ask me questions about science and physics, not about geopolitics here, please. Okay, let's take one or two more questions. Himank says, are we made of particles or waves? We are made of both. Wave particle duality. Photon is a particle as well as a wave. When it comes to the photoelectric effect, you can explain that effect only by considering the particle nature of photons. When it comes to other effects, polarization, etc., you do think of light as a wave. Similarly, all particles are fields or waves. Okay, they're part of fields, and particles are localized excitations of those fields. So waves in those fields. So we are made of both. We're made of particles as well as waves. And particles are waves, and waves are particles. That's how the quantum world works, which may not be intuitively understandable, but it is what it is. Okay. Liberal Mongol says, can you describe the structure of the photon? That's a good question, and I cannot. So, yeah, that's a good question, and that's how you stump a physicist. What's a photon? It's a wave, right? Okay, let's take it as a wave first. So it's a wave with a certain wavelength. Um, yeah, so it's a wave. It's an excitation in the electromagnetic field. The electromagnetic field is a three-dimensional field which permeates all space, the entire universe. There's only one field across the entire universe. It's here also. And a photon is a local excitation in that field. Okay, so it has a certain frequency, certain wavelength, and it is localized, but it travels at the speed of light, and it's made up of these transverse waves, the magnetic uh, transverse fields, magnetic field and electric field, that are at 90 degrees from each other, and so on. So that's kind of what a photon is. That's what an electromagnetic wave is like, and it's also a wave packet from the quantum mechanical perspective, which means it is a bunch of waves superposed on each other and localized in one place. That's the structure of a photon. And can you take a photon and compress it in a certain region? Well, that's a very interesting thought experiment, but there you have it. Yeah, a good question. I like such questions. Okay. Mubarshir Madridista says, if light has no mass, then how does the gravity of black holes affect it? It's not just the gravity of black holes that affects light, it's also the gravity of stars that affects light. When you have a solar eclipse, then you can see starlight from behind the sun visible. So the path of the light is curved. How does it happen? It's because the presence of mass curves space-time and makes the light travel in curved lines instead of straight lines. That's how it works. Okay, some more rapid fire questions. Cricket. Come on. Have you watched The Big Bang Theory? I haven't watched The Big Bang Theory, but I watched a few episodes of Big Bang Theory. It was very funny in the beginning. Exaggerated versions of physicists. It was funny in the beginning. Yes. Angad Singh Oberoi says, why are space agencies pursuing a nuclear powered spacecraft? Well, it's one way of doing space travel. It can help you reach Mars, let's say, very rapidly, and it can help you transport a tremendous amount of bulk to large distances. Let's say you want to send 1,000 tons into space to Mars. Well, if you want to do that, then you can use a nuclear powered spacecraft and use thermonuclear explosions to start the process. Yeah. Right. Um, what else? Bobby says, have you figured out new types of battery technology? What kind of technology? What kinds of batteries do we have? We have lithium-ion batteries, right? Well, you could even have sodium-ion batteries or some other ionic batteries, I'm sure. So there are other types of batteries that can be made, and sodium is a very readily available substance. As you know, it's one of the most abundant substances in the world. Uh, Go to the sea, you have sodium chloride, salt all over the place, and you can get sodium from that, and sodium ion batteries can be made. But obviously sodium is a very, it's a very, no, what's the term, it's very highly reactive, sodium. So we get complaints of lithium ion batteries catching fire well, imagine what sodium could do. But I'm sure you could mitigate this. I'm sure you can find a way around this. So one of the potential uh, battery technologies that can be explored is sodium ion batteries. Krishna Iyengar says microplastics unavoidable. Maybe there's just so much plastic out there now, waste plastic in the oceans and other places, that microplastics are just all over the place. And the future generations will have to somehow deal with this. We're finding microplastics in the blood of people. We're finding microplastics in various organs in people and so on. Is not good. Is not good. But that's what we have done to ourselves, to our environment. So there's microplastics everywhere, in tap water, in ocean water, so on. So kind of unavoidable now, and we don't know what the long term effects are going to be like. But yes, that's what we have. Himank says, how does gravity react when we reach absolute zero? No change, no difference. The temperature makes no difference on gravity. Gravity is gravity. Yeah. So when it comes to the curvature of space-time, it doesn't matter whether a black hole is cold or hot. It's going to have the same effect on the curvature of space-time. So yeah, absolute. First of all, you can't really reach absolute zero. Hypothetically, theoretically, you can, but yeah, we have never seen anything at absolute zero. But even if you do, it will make no change on the way that substance or that mass affects gravity or its gravitational field. All right. What are your thoughts on Vasuki indicus, says Arush? So they've discovered a new snake, fossilized snake, dating back, that was alive a few million years in the Indian subcontinent. And apparently it's as big as, or maybe larger than, the Titanoboa snake that used to live somewhere in Africa a few million years ago. So this snake has been given the name Vasuki indicus. So I say, great. We had gigantic snakes in the subcontinent millions of years before humanity existed. Interesting. So I'd like to see maybe a Bollywood movie with that snake being resurrected. Like you have movies about the megalodon, the Meg, and all that. So let's have a Bollywood movie with Vasuki indicus coming back to life. All right. Bobby says it's literally okay. You're talking about microplastics. Yes, it's everywhere. The bottom of the ocean, in organs. We humans have to leave a big footprint. That's what we've done, and we're still doing that. There are lots of countries, including our own country, where there's a lot of plastic waste being thrown out without being recycled and all. It all goes out into the oceans. China is doing it. There are these gigantic patches in the ocean, in the Pacific Ocean, etc. These giant patches where it's just plastic for hundreds, I don't know, tens of square kilometers and all that. And that plastic eventually breaks down, not chemically, but physically. It becomes microplastic and then it goes everywhere. So yeah, yep, plastic is everywhere. I don't see any solution to that right now. Okay, lots of questions. Let's take two more questions. Himang is asking lots of questions. What if we could transfer our consciousness into an AI model? What makes us human? Is it our consciousness or our body? Look, we don't have any definition of consciousness. Science doesn't have a definition of consciousness. Let's say I have a black box. We talk about the black box thing, right? Let's say I have a black box. How do I know if there is a consciousness inside that black box or not? Which means I have to force myself to define what it means for a system to be conscious. How do I define it? I don't have a definition. Physics doesn't have a definition. Information theory doesn't have a definition. Biology, neuroscience, chemistry, we don't have a definition of consciousness in any of these disciplines. So we know consciousness exists. When we see something, we know whether it's conscious or not. It's like life. When we see something, we know if it's living or not. I have these books behind me. All of us know the moment we look, these are not living beings. These are not living organisms, right? And when we see something that's alive, even if it's a flower, if it's a plant or a shrub, we know it's alive. We can instantly recognize that this being is alive. It's like the same thing with consciousness. When we see it, we know it. You see a cat, I know it's conscious. I see a bee, I know it's conscious at a certain level. Even plants are aware of their environment. So we know it's there, we know it exists, but we don't know how to define it. So if we can't define it, how do we transfer it somewhere? Right? Because to first transfer it, I need to have it somewhere in some data set or something, or this data set. Then how do I transfer it intact? So, it's not possible right now with current technology or with the current understanding that we have, which is that we don't have any understanding of what it is, right? So what makes us human? Consciousness or body? It's consciousness that makes us human. Our consciousness is different from the consciousness of a bat or a dog or a bear or a rhinoceros or a cat or a bee. It's the consciousness that makes us different. But what is consciousness? We don't know. We don't know what it is. Okay. All right. I guess that should be it for today. I know we have 100 more questions. Can humans see UV rays? We can't, because the equipment in our eyes, the retina, the rods and cones, etc., don't react. I mean, they don't respond to those wavelengths or frequencies of light. So that's why we don't see it. Okay, I guess we will. Om Bekerikar says, can neutron stars have habitable planets? Look, it depends on what form of life it is. The kind of form of life we have on our planet, we need sunlight to keep us alive. Without the sun, we are dead. The sun is truly our father. It gives us warmth and light, and from that, all energy comes in the planet. I mean, we eat plants. Some of us eat animals, but all of these plants and animals, they are alive because of sunlight. Plants do photosynthesis through sunlight, and then animals eat plants, and we eat animals, and we also eat plants, and so on. So all the energy on the planet, most of it, 99.9%, comes from sunlight. Now, neutron stars don't have that much sunlight. They're very dim compared to a star like the sun. So will they be able to produce, sustain a planet like ours? Maybe if it is a different form of life, it's possible. So yeah, it depends on what kind of life we're talking about. We only think of Earth-based life that we are familiar with, water-based life forms, carbon-based life forms, life in the Goldilocks zone of a star. But there could be other forms of life. So it's possible that even neutron stars may have habitable planets. You may even have some strange forms of life on the surface of neutron stars themselves. Who knows? Yeah. Okay, gentlemen, ladies, thank you so much for all your questions. I really appreciate that. Very interesting questions. And we're going to keep doing this. So every week we're going to have one science session in which we'll talk about physics, science, AI, technology, all of that stuff. So I'm going to end this session today I think I've exceeded what I had planned to do. I had planned to take 10 or 15 questions from the comments and some questions from the chat, but I've done more than that. So anyway, I'm going to end this session over here today. Thank you so much for your questions, and I will see you in the next live stream. You can attend the geopolitics history one, or you can attend the next science one, depending on your choice. Thank you so much, and keep reading about science and learning about science, and keep raising your standards. Thank you so much. I'll see you in the next live stream. Bye bye.